So in general, the closed partition function scales like this, the regular part times the singular part. So the total density here, as you can see, this part comes from the winding modes. This is because the universe is compact, and this is the contribution from the winding modes. This part, however, is the interplay between the winding modes and the momentum modes. And this R squared term, is, as I mentioned to you, is the distance between the first singularity in the beta complex plane and the Hagedorn phase. The condition is this delta omega 1 should be much smaller than 1. Okay, as you can see then, in this case, the entropy is directly proportional to energy. And from there, once you have the entropy, you can calculate the temperature. So as you can see from here, again, this Hagedorn temperature is the limiting temperature. Now we can find this thermal correlation function here in terms of T mu nu. And this is how I define my average T mu nu. So if now I Euclideanize my space-time, beta acts like my Euclidean time, and therefore the 0, 0, 0 components of the correlation function in any number of spatial compact dimensions would be like T squared, which is temperature, over R to the 2D times CV, the specific heat. So if I can calculate the specific heat, I'm basically done. So since we have the entropy, we can find the specific heat in this case. And as you can see, a specific heat in any number of dimensions, no matter what, is always scaled as R squared, for the closed strings, of course. This is not the case for the open strings. So the correlation function then scales as R to the 2, D minus 1. If D is 3, you can see this would be like R to the 4. Okay, just for the sake of comparison, this is what we found for the closed strings. This is what you would have found if instead of having compact space-time, you had non-compact space. And this is just the comparison with the relativistic massless particles, which, as you can see, it scales like that. And it's almost same for the open strings. So now if you look at the metric fluctuation, same as the way that Robert talked about it, so we'll follow the fluctuations. Now this XP is different from what Robert mentioned yesterday. This is physical distance. So the Hubble radius for a long time would be constant, and then near the phase transition from the Hagedorn phase to radiation phase shrinks to a very small size. At that time, fluctuations exit the Hubble radius and then again re-enter the radiation-dominated era. So if I calculate the dimensionless power spectrum, you can see here that the only scale appears would be like 2 to the T minus 3. So it's a simple calculation to show that you can able to scale invariant spectrum only and only when the total number of compact spatial dimensions, but large, is only 3. As I mentioned to you, we started with very weakly coupling strings. And for just consistency check, we see here, if this our result wanted to be compatible with what is observationally has been found, this length scale, which appears here, this alpha prime is basically related to the string lengths. So you have LP over LS, which is same as G string, which is the coupling constant for strings, is 10 to the minus 3, which is much less than 1. So at least this shows that we were consistent in our calculations. You can do the same thing with the tensor modes. For the tensor modes, it's rather tricky. Here what you have, in fact, for a torus like that, so it would be a change in the radius of the torus. Let me call this delta R now, while this was R. And also you have to twist the torus to get the gravitational waves. In this case also, as you can see, the power spectrum for gravitational waves scales like k to the 2d minus 3. So again, it would be a scale invariant, only if the number of spatial dimensions is 3. And from there, you can find the ratio between the tensor modes to the scalar modes. Okay, so one conclusion here is that because we found positive specific heat, by the way, we are free of forming any primordial black holes. Because the Hagedorn phase is quite long, most probably monopoles annihilate each other, but this needs to be studied in more details. And because of the long phase of the Hagedorn era, strings can go around the universe, and so the whole universe would be thermalized and homogeneous. Of course, there are some subtleties in calculations of perturbation from the thermal fluctuations that we found to relate it to the metric. So we have assumed that so far that we can use the same equations that are valid for GR. I guess my time is up, but this is just a new model. There are many things that still have to be studied in more details. But we are almost there. I guess if we can convince a few skeptics here, we are almost done. Thank you for your attention.
Yeah, first let me say this is a very interesting model. And,
by the way, we use many of your first papers on the statistical mechanics of strings, so thank you very much for that.
That's not why it's interesting. Okay. But it's a very interesting model, but I have some doubts about it, which are as follows. If you have a gas of strings, you've assumed they're non-interacting.
Weakly interacting, not non-interacting.
All your calculations are for zero coupling.
No, for very small coupling.
Effectively zero.
Okay, but still.
Right.
GS is not zero, as I mentioned to you. It's 10 to the minus 3, less than 10 to the minus 3.
Still, you're interested in the properties of the string gas on large scales.
Right.
Because the size, I don't know how big your universe is when it starts, but it must be quite big.
It's, yeah.
I mean, centimeters or something.
Right.
Okay. So, so you're interested in the properties of the gas on large scale. What bothers me slightly is that if you have this interacting gas of strings, which is chopping itself up all the time and exchanging partners and so on, I would expect there's a white noise contribution to the density fluctuations. And the problem is, if there's white noise, that will dwarf the scale invariant part on large scales.
Yeah, but so far we didn't find any.
Because you didn't include the string interactions.
That's right.
If you do...
That's right. So that's the next step we should consider. That's true.
Okay. Can you explain why the tensors came out to be small compared to scalars?
Yeah, unfortunately you were not here yesterday, so I didn't want to talk about things that Robert talked. Okay, so this is particularly because this log factor here, and this contributes, this damps the amplitude.
We have time for a quick question here.
These are two quick questions. The first is about the initial condition. What do you have to assume, or do you have to assume something about the initial condition for all this to start? And the second question is, when you end in the radiation phase, what is this universe filled with?
Okay, so that I first answer your second question. At that time, strings are followed from the equilibrium, and we think, of course, we haven't done that. Then this would be a time for the production of particles. But regarding the first thing, the only thing we have assumed, and you need to assume, is that phi dot, the derivative of the dilaton field with respect to time, should be less than 0. That's the only thing we have assumed.
Next speaker is Pinto Neto. Thank you again. Thank you.